I'm Professor Ravindranath, working as Associate Professor in the Department of Computer Science at Anand Sagar College of Engineering, Bangalore. So now I'm going to explain how to conduct CE amplifier in the laboratory. To conduct this experiment, you need power supply, signal generator, CRO and required components. So this is the signal generator, power supply, CRO, breadboard and the components. So this CE amplifier is low signal amplifier. So it requires input voltage in millivolts. So we have to take approximately anything between 10 millivolts to 15 millivolts depending upon the biasing arrangement we are going to provide to the circuit. So this is the transistor CL100 emitter base collector, and RC, R1, R2 and RE used for biasing the transistor. Biasing is nothing but applying DC such a way that the transistor will be turned on and Q point will be fixed on the DC load line. And this CC1 and CC2 are the coupling capacitors, and we know that whatever the DC we are applying here should not flow into this input signal generator. That is the reason we are blocking this DC using this capacitor not flowing into input circuitry. So you know the properties of capacitors, they are AC components, they block DC. So the DC available at this point will be blocked by this. That means it will not allow DC to flow into this side. And this output capacitor stops this DC current flowing into load. So into load we want only AC output, not DC. So if we don't connect these two, the DC conditions we fix for this amplifier will be disturbed, so that Q point will move up or down and amplification won't be that good. That is the reason we need these two. And regarding this bypass capacitor, AC should not flow through this RE because it results in negative feedback. Effectively, the VI between this point and this point will be reduced because of the negative feedback. So that output also reduces. We have the formula V0 is equal to gain into VI. So as effective input reduces here, your output reduces. Okay, so that is the disadvantage if you don't use this CE. When we use this bypass capacitor, AC will start flowing to the ground through this capacitor. That means there is no AC drop, there is no negative feedback, and our input will not be reduced. When input is constant, output is also constant. It's important to recap the circuit as shown in the diagram. This is transistor CL100. We have to identify the leads of the transistor, that is base, emitter, collector. So here there is notch, small notch on the body of the transistor. We have to count clockwise: base, emitter, base, collector. Okay, I'll repeat: emitter, base, collector. To bias the transistor, we need 4 resistors. Okay, RC, RE, RB1, RB2. With the help of this, we are going to turn on the transistor and we are going to fix the Q point on the DC load line. To conduct this experiment, we need 12 volts power supply. So that should be set from this variable power supply is 11.9. So with the help of coarse and fine, you can set the required value. So now I'm going to adjust fine to get 12 volts exactly. Stop. The 4 biasing resistors should be placed on the board the way shown here. For testing any amplifier circuit, initially we have to set the frequency of the signal generator to 5 kHz. With the help of this knob and these coarse and fine adjustments, we can set to 5 kHz. So this is the knob available to set the voltage required. as I told, for this experiment we need 10 to 50 millivolts. That is the reason we have to set this rotary switch to 0.2. So with the help of this fine knob we can vary from 0 to 0.2 volts. So that we can set from this. So if you press this read VP, so the voltage values will be displayed here. So by decreasing we can set 0.10, that is equivalent to 10 millivolts. So this is about the signal generator setting and CRO setting, power supply. And on CRO, you have to turn on CRO. And see that there is a trace on the screen, and we have to adjust that to center of the screen. So we have to place the transistor the way I am showing. So this is emitter terminal, base, collector. So emitter should come to this junction, base should go to this junction, and collector to this junction. So this completes the biasing of transistor. So now we have to connect coupling capacitors. So this is the base junction. So connect to some point here, whichever is convenient. That is CI, input coupling capacitor, and we have to connect another coupling capacitor to the collector junction. And we have to apply the input signal to this point, and we have to take the output from this point. And one more capacitor, that is called bypass capacitor, should be connected from emitter junction to ground. So here on the board I have created one VCC line and ground line. So this is called VCC line and this is called ground line. So normally we use this multiple point for VCC and ground line, because you can observe that for ground line there are so many wires are going. So two resistors, a capacitor, and all the equipment negative terminals are going to this point. So now you can check the input signal. So this is the signal generator probe, so that should be connected to this point. And on CRO you can check the input signal, what we set. So it was set to 10 millivolts. That is the reason here you have to adjust this to 10 millivolts point here and check how much is there on the screen. So here to here you have two boxes. 2 box into 10 gives you 20 millivolts. So now we have to set this input 20 millivolts constant. After that we should not vary, and shift the CRO positive to output and check there should be amplification. You can observe that input signal was so small, now output has become very big. Okay, you can see. So this is the big output. That means there is amplification. That means your circuit is working. Again I'll repeat, we have to set the input to 10 or 20 millivolts. This can be observed from the screen. There are peak to peak 2 boxes, and this white line is pointing to 10 millivolts. 10 into 2 gives you 20 millivolts. That is the input signal. We have to keep it constant. Now let us shift the CRO positive to output and see there is amplification. So input was very small. Now you can observe that output is very big, very large. So we can conclude that the circuit is working, there is amplification. So now what we have to do is, according to the tabular column given in the experiment, we have to vary the frequency from 10 to 100 Hertz to 1 megahertz in steps of 10, 20, 30, 100, 200, 300, like that we have to increase. Then we have to note down the output voltage. First I will set to 100 Hertz. So now by varying this, we can set to 100 Hertz. This is 100 Hertz frequency. So let it be 1 or 2 Hertz more or less, it doesn't matter. And check how much is the output voltage. So this is the actual output voltage at low frequencies. This amplifier gives very small output. That is the reason approximately you can take this as 10 millivolts. Okay, at 100 Hertz, it is 50 millivolts. 100 Hertz input is output is 50 millivolts. Now I'll increase the frequency to 200. You can observe that the output is also increasing. As the input increases, the output also increasing. Still, it looks like noisy. Always small amplitude signals looks noisy. You don't need to worry about that. If you go to higher frequencies, you will observe that there will be improvement in the output also as it becomes larger. Now directly I will go to 1 kilohertz and show you how much is the output voltage. So now you have to shift this to 3K and adjusting this to 1K. And you can observe that the small signal which was there for 200 Hertz is crossing the screen. That means it is becoming larger. So that indicates that amplification is there. And you can reduce this so that you can see a clear output waveform. Like this, you have to increase the frequency to 2 kilohertz, and you can observe that output is also increasing as the frequency increases. For 2K, it has increased further. Keep increasing in steps of 1000 Hertz. Now Now I'll show the output for 5 kilohertz. This is 5 kilohertz frequency, and you can note that the output is 1, 2, 3, 4, 5, 5.5 into 0.2. So that will be the output voltage. Now we will go to 10 kilohertz. It's increasing a bit. Now you can observe that 1, 2, 3, 4, 5, 6 into 0.2. So that is 1.2 volts. Okay. What was the input voltage? It was 20 millivolts. Now it has become 1.2 volts. So that means there is amplification. So like this you can, this is almost becoming constant. You can see that if I go to next frequency, so increase won't be that much. So now I change from 10 kilohertz to 20 kilohertz. The increase is not that much. So that means we are in the mid-band range. Okay. So now you can increase in steps of hundreds. Okay. So now from you can go to 100, and you can observe that there won't be much increase in the output voltage. So this is 30 kilohertz. Go back, then shift this to 300K. So now you can set to 100K. So this is 100 kilohertz. You can observe that output is not appreciably increased over 1.2. So you can measure this, how much is there. So nearly 7 box is there, 7 into 0.2. So that gives you 1.4 volts. Okay. So for 10 kilohertz, it was 1.2 volts. For 100 kilohertz, it is 1.4 volts. That means only 0.4 increase is there now. So after that it becomes constant. You can observe even if I shift this to 300 is almost same. So go to next higher frequency range. So this is I'll show one reading for 500 kilohertz. So this is 500 kilohertz, and we can observe the output is almost same. No, it's not increasing. That means it has reached constant level. And if you try to increase further frequency above 500 kilohertz, you can observe that output will start decreasing. You can observe that after 600 kilohertz, the output is start decreasing. So this is high frequency response. And we can go up to the maximum frequency available on the signal generator. Now we have set the signal to 3 megahertz. For that, this is the output voltage. And we can measure the last reading. So there are three divisions, 3 into 0.2. 0.6 volts is the output voltage. Okay, this is how you have to conduct the experimental CE amplifier. The other name for this amplifier is RC coupled amplifier, because using R and C components we can make this circuit. Particularly the CE amplifier is an voltage amplifier. Wherever the voltage amplification is required, we can use this amplifier. But this amplifier is not suitable for impedance matching purpose, because input impedance is not very high, output impedance is not very low. That is the reason it is not suitable for impedance matching purposes, but it gives very good voltage gain. To measure input and output impedances, we need a decayed resistance box. To measure input impedance, we have to keep the DRB values to 0. That means we have to turn all these pointers to 0, so that DRB value will be 0. So now the total resistance of this DRB is 0. We have to insert this in series with the input circuits. So the way I am showing, we have to do that. Open the input terminal, connect one end of DRB, and to the other end we have to apply the input from the signal generator. And for measuring input and output impedances, we can set the frequency to 5 kilohertz. So this DRB is not giving 0 signal. So let me check whether so there is no output. That means this DRB is not functioning properly. So let me see the input. Okay, now it's fine. So you can a halt until. Okay, start. So as I told you, the DRB value should be 0 such that we are going to have some output voltage. So now we can count and check, just if you count the number of boxes that will do. So here to here we have 4 boxes. Now we have to increase the value of resistance such that it becomes half of this value. That is, we have to adjust the DRB value such that it becomes 2 boxes on the screen. So we have to start adjusting with smaller values. Now roughly here we have 2 boxes, that means we have made 50% reduction in the output voltage. Now we have to measure the resistance on this DRB, that gives you the input impedance. Now it is around 4K. So this is 0, we have to add these all knob values. So this is 0, this is 0, then this is at 4K and this is also 0. So input impedance is 4K, 4 kilo ohms. So this is about input impedance. To measure the output impedance, we have to keep these DRB values to maximum. That means resistance should be very high. So turn all the knobs to 10, 10, 10, 10 here, and also 10 here. Now we have to shift this DRB to output side. For input measurement, the DRB was in series. Now we have to connect the DRB in parallel to the output circuitry of the amplifier. We have to connect back this signal generator to CI. And again you can observe that there should be 4 boxes. It is 4 boxes. Now the resistance is in maximum. We have to decrease this resistance so that again it becomes 50% of the maximum value, that is to 2 boxes. So you have to start adjusting from higher value. So this is, you can observe that this is kilo ohms value, so you have to decrease this. You can observe that there is slight decrease. Then the next higher value should be decreased. You can adjust and see, is it 50% reduced? Yeah, now it is 50% reduced. Now we have to measure the value from this DRB. So this is at 0, this is also 0. Now this is around 500 ohms and this is another 100 ohms. So totally the output impedance will be this plus this, 500 plus 100. 600 ohms is the output impedance. So this is how you have to measure input and output impedance. I'll repeat once again. We have to connect the DRB in series with the input circuit, keeping the DRB value to minimum. Then we have to increase such that the output reduces to 50%. In the same way, we have to keep the DRB value to maximum, connect in parallel with the output circuitry, keep decreasing until the output reduces to 50%, and that value will be the output impedance of this amplifier. So this is how we have to measure input and output impedances. For higher voltage, that's the reason this looks very small. So keep increasing, there will be sine wave. Okay, so there is a small input signal. Now shift the positive of the CRO to output. It should be amplified, no? That means it should become larger than what it is now. So input is smaller. See. It has become so big. Okay, so it has gone beyond screen. So reduce this. Now we can conclude that this amplifier is amplifying the input signal, right? Yes. So this is what you have to test the circuit first. First you have to test the circuit before taking the readings. Make sure that your circuit is working as an amplifier. So then you can vary the frequency, note down the output voltage. So we are going to keep the input constant, I told you. Then using formulas you can calculate V0 by Vi. Okay, Vi is constant throughout. Only V0 from CRO, it will be different. So gain is also different. Then you can to plot the graph using anti-log semi-log graph sheet. We have to calculate the gain in decibels. That is nothing but 20 log of V0 by Vi will be the dB gain. So just normal gain is V0 by Vi. dB gain is 20 log of V0 by Vi. So using those values versus frequency will give you the graph of this amplifier, okay, on semi-log graph sheet. And input and output impedances the way I showed you. So carry on.